Hello my dear students, I am B S Pandey, your physics lecturer. My dear students, today in series of Standard 12 video lecture, we are in lecture number 82 and we will study a very important topic. It is LC oscillation. This particular topic is important for the point of view of examination, CBSE as well competitive exam. Alright my dear student. So let me start this particular topic. We will study a mechanism of LC oscillation, and one thing I will include a very short clip that might be very helpful to understand its mechanism and application. Alright my dear student. Here we are in lecture number 82, and basically in this mechanism we will study the name LC oscillation. It means the oscillation of not the particular device actually, but the oscillation of energy only. Energy oscillates from one device to another device. Okay, we will discuss in very detail. Let's start today's lecture. It is lecture number 82. Lecture number 82 of chapter 7 NCERT, alternating current. I hope you have watched my previous videos for more clear idea about this particular topic, that is LC oscillation. LC oscillation. One thing I would like to clear again my dear students, oscillation of what? So here we will talk about the oscillation of energy. We will have the energy in one device, that is the capacitor, and it will drain down and move to the inductor. After the capacitor fully discharged, again to oppose the change in flux, inductor supply the current which charges the capacitor, and inductor discharge. Alright, and this exchange of energy between these two devices is called LC oscillation. Alright, but initially we need at least one device fully charged. Alright, and suppose the energy in the system it is E, it remains same while the exchange between these two devices. Remember, if the total energy it is E, so the energy you will sum up, you will get the sum up from these two devices, you will get the E, but there is loss of energy, then in that case you will find energy goes on decreasing, and that case will be something different. We will discuss. The two case, it is undamped and damped oscillation of the energy. Here we are considering the undamped oscillation of energy. Alright. So what we are having actually, try to understand, we are having the two devices. Okay, at t is equals to 0, we are having one capacitor and it is fully charged, plus Q and minus Q. Remember, it is fully charged. In this capacitor, the energy is completely filled. Alright, and we are having an inductor which have no any energy since it has not connected with circuit. This is the storing device, but it can store the energy if it has been not connected with a battery. But it stores its energy in presence of electric field, or you can say energy is stored in presence of electric field. But it stores the energy till it connects with the source. Magnetic field changes current poses by this device. Alright. Anyway, this is the capacitor C, this is the inductor L. Let me recall you my dear students, we have studied the energy across these two devices. The energy across capacitor in terms of charge, we know that here the E in capacitor it is Q square over 2C. where this Q is the maximum charge of the capacitor, and in this inductor, energy in this inductor, it is half Li square. This is the maximum current 10 with this inductor. Remember, my dear students, it might be that you will face in certain books, it has been written this E as the energy in presence of electric field, or it can be written as this U. In presence of electric field, it is Q square over 2C, and this is the energy in presence of magnetic field, half Li square. Don't be confused. Alright, this is the energy stored, potential energy stored. This is the energy stored in presence of magnetic field, in presence of electric field. Now, my dear students, what we have to do, actually initially one device is fully charged, we are going to connect with the inductor. Alright, so let's connect this device. When you can write, my dear students, when capacitor is connected, fully charged capacitor, in which the charge, total charge, it is plus Q. Alright, on the other plate it is minus Q, maximum charge is Q. Fully charged capacitor connect with the inductor. Alright, yes, this one. Let me draw the circuit. You can connect here the battery also to represent this capacitor has been charged by that battery, but you know very well, as I have told you, so you don't worry about this one. Here, let me draw this diagram a little bit bigger one to explain the concepts. This is the inductor. Alright, yes. Plus Q minus Q, alright. And the capacitance C, inductance, it is L. Initially, the total charge, that is the energy, it is contained with the capacitor. So you can see the polarity of capacitor plus, 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 minus, 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 and this plus or minus representing the total energy stored with the capacitor. If there will be energy appear on this inductor, I will represent that energy with the help of magnetic field lines. Alright, my dear students, I will represent with the magnetic field lines. To represent the energy, initially the energy having this capacitor, so at T is equals to 0, we will use energy diagram. Alright, we will use energy diagram. Here, look at here, the total energy having the capacitor, this one is representing the energy level diagram. This is energy with the capacitor, that is in presence of electric field, and the energy of inductor, here no energy. So to represent the very negligible, very small value, I am representing here with the red one, and this will be the energy in inductor. You can say here it is the maximum here, and it is 0. Alright, that is the minimum. Now what will happen? After some time, this capacitor leaves the charge starts flowing in the circuit. As soon as it is connected, the key connects, charge starts flowing. As the charge starts flowing, current build up, and due to change in current, the current build up, and once the total charge discharge, that is the total charge transfer, it retains the maximum current. Alright, it retains the maximum current. But after some time, when it discharges completely, the current becomes 0. But after some time, let me draw the circuit here. Let me draw the circuit over here. After some time, this is the case 1. At any time t is equals to 0, that we have discussed right now. Alright, my dear students. Now, after some time, what will happen? Now it looks like this one. This is the capacitor connected with inductor. Of course, now the energy is Q, suppose, which is not the maximum value because energy has been transferred. Some energy has been transferred. Alright. Now I am representing here the charge little smaller value because some charge has been transferred. You can see here the charges are maximum and here the charge has been some transfer. But remember, as the charge has been transferred, what happened? The current build up in this one, and due to current there must be some self-induction and EMF induced. So there will be the magnetic field lines. Alright, there is a magnetic field lines. But this magnetic field lines is not very much. You can represent the magnetic field line. It is a closed loop, but this is not very much. But in this case, my dear students, what will happen? There must be some energy with the inductor also. It might be the energy having the capacitor. Of course, this capacitor have some energy, but after some time, after this case, in this case at any time t, at t is equals to t1, after this 0 time, this capacitor will have the energy as well as the inductor. Actually, what happened, my dear students? Energy goes down of what? Capacitor, which was stored in presence of electric field, and energy through this inductor increases. Alright? Yes, it increases. This is the energy in presence of how much energy we can write, my dear students. So look at it. If the current established, it is the I. Alright, so we can write here the energies. If the charge is Q, then this is energy equals to Q square over 2C, and here at any time T, the current, if it is I, then it can be written the half L I square. Remember, this is the energy in this inductor and energy in the capacitor. What will happen after some time? If we allow to move the charge further, and then the charge completely vanishes over the capacitor. Remember, since charge is discharging rapidly, there is an increase in current, and this increase in current never except by this inductor that we have studied already. After some time, when it is fully discharged, what happens? It will oppose the increase in current and start giving the reverse, that is the back EMF, and then this will start charging the capacitor. It works as a battery, that is the source for the capacitor, and start charging again this capacitor. But before that, it has been discharged completely, and that will be represented by this diagram at any time t2. At any time t2, my dear students, what we can write here? This is the capacitor, inductor. Now this capacitor has no charge, and the current which was established almost gone, but the magnetic field lines here, it is maximum. It is, yes, it is the maximum. The total energy now comes to this inductor, and we can represent this energy diagram. This capacitor having the very low energy. To represent this one, I am representing this as the very low energy with the capacitor, and this one is the energy with the inductor. It goes to its maximum value. This one, energy with the inductor, which is the maximum. Now this energy goes. What will happen, my dear students? Now, this energy actually start oscillating. If this reach to the maximum current, it will start opposing because the maximum changes this inductor to not like and start opposing to the flow of current. Now in this case, you can see this capacitor and inductor. This capacitor and inductor. Now it starts charging by the back EMF to this capacitor. Again, here the charge appears like this situation. Remember, like this situation. In calculation, we will try to understand how much time required to become the energy equal, how much time it required to become the energy zero in capacitor, energy zero in inductor, and in complete cycle what will happen. All the things we will draw by the graph after the calculation. But here I am representing you, I am explaining you the mechanism of Lc oscillator, that is the oscillation. Alright. I hope now, my dear students, you can draw the graph by yourself. Now this time at T3. Alright, at this time, again, this energy increases, but the energy by this inductor goes on, decreases. Alright, UB or EB, you have to understand, my dear student. Energy goes on, decreases. You can represent the fill lines. The first situation you can see. Now what will happen? Again, this will charge the capacitor to its maximum value after giving the back EMF. But remember, I will draw the diagram as the first case. It was at t equals to 0 second. You can draw by yourself. Alright. Now, in this entire situations, what you have noticed the energy oscillates from capacitor to inductor and inductor to capacitor, and it goes to the infinite time when there is no resistance in the circuit. Because resistance, remember, this is the resonance condition. If there will be the resistance, what will happen? Some energy lost, and after each oscillation the energy becomes smaller. After each oscillation the energy becomes smaller, and there will be some time at which the energy of this system becomes zero and is stopped oscillation, and that will be considered the damped oscillation of the energy. But here in this case, if the system is ideal, which is not practically possible, but we are studying here the practical, impractical thing. Okay, impracticability, this has no practicability, my dear students, and in this ideal situation, there is no resistance and no energy lost. Alright. So now, my dear students, to understand this mechanism more perfectly, I am going to include here a very short clip, my dear students. Then after, we will do some calculation to understand the LC oscillation and the graph of the quantities, that is the energy by this capacitor and inductor. So enjoy this clip, my dear students.
If you connect a charged capacitor across an inductor, you will see a beautiful energy exchange take place between the two elements. These energy oscillations look as if the capacitor is saying, "You take the energy," and the inductor then says, "No, you take my energy." Why don't any of these elements store the energy and become settled? Let's have a look at the interesting physics behind these oscillations and some of the applications. Before diving into the LC circuit, we need to understand a simple circuit, a capacitor-resistor circuit. The capacitor is fully charged initially. Let's introduce a resistor into the circuit. Here you can observe that initially the current flow is at the maximum and then it sharply decays with time. This is expected because at the beginning the charge difference is at the maximum, so the current has to be at the maximum. Now let's see what will happen if the resistor is replaced with an inductor. Here again, the capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning, and then the current flow would reduce as in the previous case. However, this will not happen in practice. An inductor develops EMF across it, based on the change in current flow. This means that a drastic change in current is not possible across the inductor as in the previous case. Now the current flow starts from 0 and increases to the maximum, and then comes back to 0 again. In an inductor-capacitor circuit, the current flow variation has to be gradual, and here we can see that the current flow in the LC circuit is shaped like a sine curve. Let's look at the electron flow animation once again. The current in the circuit starts from 0 and gradually achieves the maximum value. In the next 1/4 of a time period, the current from the capacitor starts to decrease, resulting in another change in current. At the end of the capacitor discharge, if you check the EMF across the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. In the next half of the time period, the capacitor will be fully charged with the reverse polarity. This also means that the current flow will be in the reverse direction for the next half. Hence, in an ideal circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillations of energy. However, practically, we can never achieve such ideal behavior due to the presence of resistance. The resistance causes energy decay in the form of heat. This means that in a practical circuit, the oscillations will die out eventually. As we increase the resistance, the oscillations die out very quickly as shown. If we increase the resistance further to some critical value, there would be no oscillation at all.
I hope, my dear students, you enjoy that clip, and there must be some concept more clear about this LC oscillation. Okay, now let me do some calculation to understand the frequency, with which frequency actually this energy oscillates. First and second, if the total energy remains constant, there is no resistance in the circuit, alright, then how the energy actually, with which function, in which form this energy oscillates. Here, my dear student, this is the capacitor at any time, in which in this capacitor we are having the charge at any time t. Remember, I'm not talking about the maximum and any other thing. Inductance, it is L, capacitance, it is C, which is constant. Alright, so we are going to study here the energy of the LC oscillator. Alright, energy of LC oscillator and its graph. Alright, so at any instant, at any instant, my dear student, if we write the energy in capacitor as Q square over 2C and energy in inductor as half Li square, then what will be the total energy, which is constant, and it will be the UE plus UB, that is Q square over 2C plus half Li square. Alright, my dear students, if we will differentiate this equation, what we will find actually d over dt Q square over twice C plus d over dt, this is with respect to time, half Li square, and the constant will differentiate for the 0 value. My dear students, listen carefully. Thus twice 1 over 2c is constant and q square, it is 2q dq by dt. Could you write? Yes. Here 1 by L by 2 it is constant, L by 2 it is constant, and I, it will be the 2i di over dt. This is 0. Look at here. This 2 will be the cancel out here as well. Q over C dq over dt plus I, it is nothing but the dq by dt we can write, and this di by dt can be written as d2q over dt square. Could we write? Yes. I, it is dq by dt, so it will be the d2q by dt square. Now you can see here, sorry, I think we have left L here. Yes, this one is the L. Alright. So we can take this L dq by dt as common. L dq by dt as common. So we'll have Q by Lc over here. Q by Lc plus here d2q by dt square. Am I right? Yes. Now look at it carefully. We are moving towards a very interesting result. Minus, this will be 1 by Lc times Q. My dear students, this is the equation 2. Try to recall and compare this equation that you have studied already in simple harmonic motion. Can we write this simple harmonic equation as, we know that d2q, let me write the simple harmonic motion that you have studied in your standard 11 in the same form that you used to write over there. Alright. Yes, look at here. d2y over dt square is equals to minus omega square y. Did you recall? Yes. And the solution for this equation, I hope you remember solution of this equation as, that is the y, it is a cos omega t plus phi. This was the solution of this equation. The same we are going to use here. So, look at here carefully, my dear students. If we'll compare equation 2 with equation of SHM, so we can write, my dear students, at the omega square, try to compare this minus, so here the function q, here the y, this is y, so q and q, so 1 by Lc will be equal to the omega square, 1 by Lc, and this omega square will be 1 by root under Lc, that we have studied already. This was the frequency, do you remember? Yes, so this is the frequency of Lc oscillator. Kindly note down, this is the equation of oscillation and oscillation of Lc, that is the oscillator. This is the frequency of Lc oscillator. You can write here the omega equals to 2 pi f also. So you will have the linear frequency. Okay, my dear students. Now, listen carefully. If we are having this as the omega, what will be the solution of this equation? What will be the value of q? Q. Here we can write the q as q naught, as it was the A amplitude. So the amplitude of this charge, this q naught is the amplitude. Remember, my dear students, it is the amplitude. Yes. And cos omega t plus phi. We can write. Okay. Now try to understand. If we'll try to write the equation for the energies, okay, in capacitor as well as the inductor, then we can write here energy in capacitor as U in presence of electric field, it was Q square over 2C. Here the Q we are having how much? It is Q naught, that is Q naught square cos square omega t plus phi divided by 4C square. Am I right? Yes. If this is the function of time, with the time, if this charge is changing, as you know that charge increases and decreases from the capacitor, it charge and discharge. So with the time it changes. And this cos sign representing the charge changes sinusoidally. We can represent this one over the graph as well. But once if we will have the equation of both the energy, then it would be easy for us to represent both the energy over the graph. So let me find the energy through inductor. U, in presence of magnetic field, it is half Li square, half Li square. From here, this charge we can write the current first. Let me write the current from this equation. Okay, so this current will be I is equals to dq over dt, and we can write here the q naught and d cos omega t plus phi over dt. It will be, my dear students, minus q naught omega sine omega t plus phi. I hope you understand. This is a very simple differentiation. Now we can write the energy in inductor in presence of magnetic field is the half L I square. This is the current. So this minus will be the positive. Q square, Q naught square, omega square, sine square omega t plus phi. Alright, this is the very important one energy, this one, and another is this one. Now look carefully this equation, my dear students. You will find that both the energy is changing sinusoidally. It is the sine function, it is the cosine function. At time t equals to 0, this value will be almost 0 if there is no phase difference between these two, or the phase difference 180 even. Alright, so this will be the energy at t equals to 0. Energy is 0. From the equation you can see clearly. Of course, at t equals to 0, total energy, it is stored with the capacitor. From this equation, my dear students, you can see at t equals to 0, the energy, it will have the maximum value. If this phi is 0, then this becomes 0, and this is the maximum, q naught square over 4c square. Now, could you represent this one over the graph? Yes. Look at here. At t equals to 0, if this is the time, alright, this is the time, and thus we are representing the energy. Alright, we are representing the energy. Then the graph looks like, for the energy with the capacitor, it should be start from maximum cosine value. And what with the amplitude? It is q naught square over 4c square from here. If, my dear students, in your mind, remember this, so the parallel, because amplitude is not going to be changed, it is not damping. My dear students, it should be very clear in your mind why I have plotted this graph over the positive of the axis along the y-axis, because this is the square function of cosine, and cosine value lies from -1 to +1, because but the square will be the positive, and this is the particular graph. Alright, so this is the graph for energy through capacitor. Through inductor we can write the graph. It starts from 0 and looks like this one. Now, my dear students, you can have the analysis, which is very simple. This is the time, look at here, this is the time from here to here, it is t by 2. And if it is t by 2, then this is t by 4. Am I right? And if it's t by 4, then this time will be the t by 8. T by 8. Now you can see, my dear students, both the graph is meeting here. Actually, the graph is not very specific. If you will draw the straight line, all it will meet at the same point. Okay. So at this point, both the energy is similar. You can say. Try to remember the graph. Actually, we were representing like this way. So at the same level, the time, it will be the t by 8. Whatever may be the time period, we can calculate from the equation. It will be given in the question. So the time at time t by 8, this might be the MCQ question in your examination. Remember, students, at which time the energy of inductor and capacitor becomes same in LC oscillator. So the answer will be the t by 8. You can see here the t by 8, it is the time at which the energy become same through both the devices. Alright. Now, other time also you can study at which time it will be the maximum, at which time it will be the zero. Alright, my dear student. So this is the concept of LC oscillation. I tried to explain this LC oscillation in this one lecture. Okay, my dear students, I hope that you understand the concept. Otherwise, we will discuss in the group. So this is all about today's lecture, my dear students. Thank you very much.